we have to continue with solving the planetary motion of the solution of a motion in a central force field, and I think we stop here. That remember we wrote the equation of the orbit. So the orbit is we have two coordinates: the distance from this central force that only depends on that distance, not on the angle, and then the angular coordinate, right? Because by using conservation laws, we already reduce a three-dimensional problem to a two-dimensional, and then you have just two coordinates. In fact, if we have time, I will show you that in addition to the total energy and the angular momentum, there is another vector that is conserved in this problem. So that it's kind of interesting, even though it's not completely independent. So it doesn't. But anyway, we wrote the equation for the orbit as an integral by integrating the equation of motion, and I write it back here. So it's an integral over r, and then there was r squared, then you have a square root, and this is just a constant that depends on this constant that come from the conservation law of the energy and the angular momentum, and then you have 2mv L square 1 over r square. Now there was this factor of 2 that I didn't have time to check. Maybe you did. Is there a factor of 2? No, you forgot as well. Okay, so we use this very useful normalization in which pi 2 are equal to 1. Okay, you know that it's an easy way not to make mistakes. That's a joke. And then I said you have to tell me what the potential is, right? Because at this point you cannot do this integral unless I tell you the dependence. And I said if you take a potential that it's a power law that you can write like a constant r to the n plus 1, this is just, I mean, the convention to write it. Then the interesting thing about this integral is that for certain values of this n, or in other words, for certain values of the power law, we do know how to solve this integral exactly, okay, meaning that you find the solution in this book where you have all the integrals and in terms of special functions. And in fact, for n equal to 1, minus 2, and minus 3, it's even better than that, because the special function in terms of which you can write the solution is a trigonometric function. So it's even, I mean, well, okay, you are familiar with those functions, and then we concentrate now today on the special case in which, in fact, this is the Kepler problem, okay, in which the potential is minus k over r, okay, is an attractive force, okay, so minus, and you see it's the case in which you have r to the minus 1. So it goes like 1 over r. We already discussed kind of this potential, but now we want to. And because of this property, I expect to be able to write the solutions, that is the orbit, in terms of trigonometric functions, okay? And that's in fact what happened. So so I can replace here, right? I can write. Okay, let's write it here. let's write it in terms of this u. So this is minus ku, where u is 1 over r, right? That makes this integral simpler. So and here I forgot that I also have a constant. So let me write it. Theta over r is this constant, okay? Then I get the switch of sign because of the change in the integration variable du, and you see I can write it now 2me L square. Now this becomes plus 2mk, right? U minus minus, right? L square minus u square. So now you see this integral here is in the form that you find in the book, in the tables of integrals, and is in this form here, ax square. No, let me write like a constant, plus bx plus c. Okay, just let's say general. So this is the integral you find in the book. Did you find this book in the library or not? This Ridskin Greifstein. It's a thick book with all possible integrals. That's I think you should have it. It's nice. You know, you find an integral, you go to the book. Or you can use Mathematica. Anyway, these are called the tables of integrals and series, or no, all this kind of information. It also contains all this property of functions, like the sine of alpha plus beta is equal to the sine, you know, that. And of course, as I said, all these integrals are by now mapped into this program Mathematica and other similar software. So, okay, if you are lazy, you can just use that and not go to the library. By the way, how did they compute all these integrals? I mean, Mr. What?
They use some transformation.
But more generally, I mean, you know by now, I mean, you have done complex analysis, right?
Yeah.
So you know that all these integrals, I mean, if you find some clever path into the complex plane, usually you, through the residues theorem, right? This is the way they Ridskin and Greifstein, these two Russian guys wrote this, and all the people before them. I mean, in a way, this is the reason why you study complex analysis. I mean, essentially, it's useful because it allows you to do these integrals, because you know that in the complex plane there are many powerful theorems. I mean, it's much easier to study functions there. I mean, right? Because if you know a function in a very small neighborhood, then you know the function everywhere in the complex plane. On the real axis, no, this is not true. You only have the Taylor expansion, but and because of that, you have all this theorem about the residues, and so you are able to do all these integrals. So that's the reason why in the 1800s they start studying complex analysis. I mean, anyway, you go there and you find that, okay, so you look for this kind of integral. So it's an integral of 1 over the square root with a quadratic polynomial outside. So all you need is to identify. In fact, I mean, this you find in the table, and you see that this is equal to minus c, the arc of the cosine, so the inverse function of the cosine of minus b plus 2cx square root of b squared minus 4ac. So all you need is to know what is A, what is B, and what is C for your case, and then you have solved the problem. By inspection, you see that A is 2me L square, B is the coefficient of the linear term, so it's 2mk L square, and C is minus 1. So you see that here you just get 1, and then you can plug in. And if you do that, I have my solution that is this arbitrary initial position, right? It's somewhere on the orbit that you start looking at the planet, minus this arc cosine. So I plug in the values. So you see B, and so I get, I guess, if I did it right, or if you want to go back, now let's go back to the 1 over to the r distance variable. This is also, so you see, then you have u, okay. So let's and I also want to write it the usual way. I want to write r as a function of theta. So I multiply by this, you see. So I get, so I take 1 over r. So let me write the result, and then if you don't believe me, we go through the steps. Right, so I have this term here. So I take theta minus theta naught, then I take the cosine. So I get the cosine of theta minus theta naught. The cosine of the r cosine, by definition, is whatever you have inside. So whatever I have inside is this thing here. So here I have this interesting combination. I'll come back to this in a second. And as I say, I have cosine of theta naught. So this is the equation of the orbit for the Kepler's problem. So this is orbit, or orbits actually, because you can have all kinds of orbits, as you will see in a second. Solutions of Kepler's problem, that is the same thing of the central force given by this very particular potential. That, of course, if you take the derivative, is 1 over r squared, and this is Newton's universal law of gravitation. Okay, so that's the solution. Do you see how you go from here to there? No? So take, as I said, take this on the other side and take the cosine. This gives you the cosine. You take the cosine of the r cosine. This is like x times 1 over x is just whatever you have there, because this is by definition the inverse function of this. So you get all this stuff. I take this, I multiply by the cosine on both sides, so I get this factor, square root of the cosine. And then the 1 goes on the other side, and then I want to pull out the u, that is 1 over r, and I get this coefficient. Do you see it now or not? Just arithmetic, I guess. Okay, so that's a very nice... No, you... What? This arithmetic stuff. So then come out, you do it at the blackboard. You try. So we have now, we erase all this stuff because we... So take this on the other side, right? So you have theta minus theta naught equal minus whatever is there. Then I take the cosine of both sides. So I take cosine of this. So this is gone. I take the cosine of these things here. So the cos of r cos, so it's like, right? So I have here s square u mk minus 1 divided by the square root. Now I multiply the square root, so the square root goes here, right? Then that takes the 1, so I have 1 plus square root that I have here, and then I multiply by mk divided by l squared, and I have u equal whatever is there. U is equal 1 over r. I have this. One more time, or okay. So this is it's a very powerful result. I mean, people have been, they work for thousands of years, literally, to find this. That is the orbit of the sun, or if you wish, of the Earth around the sun, right? I mean, so we'll come back to this. First let's discuss. You see, I wrote orbits because here you have a family of orbits, and they depend on whether this coefficient is larger or if it's so. Let's give a name to this. I think usually it's called the. Is this the eccentricity? I think it's the eccentricity. Maybe. Yeah. Anyway, let's call it E. So you see, we have a general equation that is 1 over r c 1 plus e, where e, I define this. The c is going to be this coefficient, but that's not really essential, cosine of theta naught. So that's a family of curves. They are given by a trigonometric function as advertised before because of the simplicity of the problem. And I think this is called the eccentricities usually. And depending on whether this eccentricity is larger, equal, less than 1, or even equal to 0, you have different curves. What are these curves? Well, these are well-known curves. They are well, they were known because they have been studied for many years back to the ancient Greek masters of geometries, in particular Apollonius. This guy studied. Do you know these conical sections? Have you studied those? I mean, if you take two cones, you know a cone, no? It's like. So it's infinitely, but let me draw it like this. So something like this, right? This is a cone, and I put another cone on top of the first cone. Now, if you take sections of this solid, it's in 3 dimensions, okay? You see that you look at the intersection between these two geometrical functions, you generate different curves, right? Because if I take a section like this, so I take a plane. Now this is a cone, so it's the surface designed by this cone. It's like a ice cream cone, you know. Okay. And this is like with a knife, you cut the ice cream cone. Okay, not nice, but if you cut it this way, the curve designed by the cut, what is left, right, is a circle. So that's a figure, a geometrical figure. They like it very much, the Greeks, the ancient Greeks, for some reason. But you see, you can cut it also in a different way, right? You see, right? For instance, you can cut it not orthogonally, but the plane goes like this, right? Then it's going to be not a circle, but an ellipse, right? It goes like this. And you see that there are other possibilities, because, for instance, you can cut it with a plane that is parallel to one of the side of your ice cream cone, right? And then that would be a hyperbole, right? Because you see, this is a special ice cream cone that goes all the way to infinity. So I guess you don't have any ice cream because it's all cone and no ice cream. But okay. So you generate all this. You generate a circle, a parabola, ellipses, and hyperboles. Okay. So the Apollonius study. In a way, he was able to bring together these very different curves under this construction. They like geometry, so they construct all these things geometrically, okay? For us, this is a very old-fashioned way, even though it's beautiful. And for us, this construction is really encoded in this equation, because according to the value of this E, you can have, for instance, take E equal to 0, okay, trivial case. You see that you have a circle, right? Because 1 over R is a constant, that means R is a constant, so you have a circle. Now, so let me write down. So this is called the eccentricity. And if you have E greater than 1, you have the case I draw here, the hyperbole. If E equal to 1, you have a parabola. And if E is negative, okay, you have the ellipsis. And if it's exactly equal to 0, you have a circle. Okay? But you can, in our language, you can translate this geometrical condition in terms of your parameter, the energy and the angular momentum. And you see that actually, let's just look at the energy, okay, given the angular momentum. You see that in order to, so this E is 1 plus something that depends on the energy. So if you want that something to be larger than 1, you need the energy to be positive. So remember that the drawing that you remember, right? That the effective potential, and then you take value of the energy. You see that this is reproduced here, because this was the 0. So if you have energy positive, you remember the particle was like a comet coming in from infinitely away and then going the way, so that was the orbit. If you want to have E equal to 1, you see there, right? You need exactly 0 energy. And if you want the E less than 1, you see that you have to make this quantity less than 1, so the energy must be negative. And this fixes the energy to be exactly minus the inverse of whatever you have there, so the energy, you get the circle. So you see, matches exactly our qualitative discussion. We already knew that you had 4 different kind of orbits, well, at least 3, and we matched that with the value. So this was the effective potential, this is what the energy, and you see this is reproduced by what we found there. If the energy is positive, right, we had the unbounded motion that correspond to the hyperbolic motion of the parabolic motion, the first 2. The parabolic is the one exactly at 0. And then going down, for negative value, we had this solution going between these 2 values, right? Remember, you remember, right? And you see that it doesn't go crazy like that. Actually, it just is an ellipsis, so it's well behaved. And we also found that for a very special value of the energy, the one that matched exactly the minimum of this curve, you had the circle, and this corresponds to this very special value of the initial condition that makes the eccentricity equal to 0. Okay. So now, so we came full circle because this was our starting point, the qualitative analysis of the orbit, and now we have the analytic expression for the orbit that is this one here, or better, this one down here. So now that we have solved Kepler's problem, we can, well, what can we do? Well, we can try and discuss the motion of the planets as seen from the Earth. First, let me say a few words about this other, yeah, I think we have time, this other conserved quantity. So how it's easy to discover in, so I guess I can erase here. So this is more like a footnote, it's not that I make. If you look at the motion in a central force problem, so that means that if I write, let's do it using Newton's law. So what is Newton's law? Newton's law tells you that the dot of the p, that is the m acceleration, is equal to for a central force is equal to some function of r pointing in the direction of the distance. So this is like a unit vector, right, pointing in whatever direction. So this is a general way I write Newton equation for a central force, by definition, okay? We all agree. So now I consider I take the vector product of my acceleration, or my force, really P dot, times the angular momentum that I call big L. I know that because it's a central force, that big L is conserved, right, because of Noether's theorem. So let's do it. This, by definition, is what? Is just R cross P, right? So let's just do it. Yeah, I don't know whether to pull out an M. Okay, no. So let me rewrite it. So I have. So this is M, right? So M F R over R, R cross R, R dot. Why? Because, right?
Because P is M R dot, so we pull M out and then.
Yes. You see? Just use this is a triple vector product. So let me write it as R. You know, if you have A cross B cross C, this is A, then R dot R dot, okay, minus R square R dot. You remember this? Otherwise, in the same book where you find the integrals, you also find that. Okay, so this is r dot, but this is like 1/2 d dt are the lengths of these things, right? Okay? So now I want to take the time derivative of this quantity, okay? And you see that, so dt of P cross L, now L is a constant, so I only need, I have to take the time derivative, so minus m f r, r square. Let me write it this way. I pull inside this, and then I take the derivative here, r minus r, then r dot r square. Okay, by using what I just erased. And then you see that this can be collected, because this, you see, this is r dot, then it acts on r, so the whole thing here is just m f r, r square, dt of r over r, right? Because you see, first it acts here, and then on 1 over r, and you get the other term. So you see, you have identified a combination that is going to be it is going to be a constant if now I plug in the special case of Kepler's, in which this f of r, right, is just what? Right, because in the case of Kepler, the force is just k minus k over r squared, right? So for this case, I just get m k dt of r over r. So I cancel out that. It's k r squared, it's the force. So you see, if I take the time derivative of this minus this, by definition is going to be 0, right? Because if I consider the time derivative of P dot cross L minus mk r over r, this is equal to 0. I just pull the right-hand side to the left, and I write that combination. This combination is called A, and is the Laplace range length. Well, I needed 3 people to do this vector, and it's conserved for the Kepler problem. So this is an additional vector. So beside E and L, also A is conserved, but you see that it's not a completely independent one, because you see it's part of L is in the Laplace range length vector. So this vector is a constant of the motion. That's nice to know. I mean, everything that is constant is nice to know. Can we visualize that? I mean, what is constant? Yes, we can, because we have the definition of the vector, so we can. So for instance, if I look at the Earth going around the Sun, now I know that this should be something like ellipses, and the ellipsis is, so the Sun is roughly in one of these points. So you see, this vector, how is this vector? Now, if I compute this vector here, what is the direction here of P? Sorry, here because I'm taking the derivative, there is no, right? This is the vector. Because I'm taking the time derivative, right? This is constant, so I pull it out. So how is the vector here, for instance? Where is the direction of P cross L here? This is P cross L here is a vector pointing this way of some lengths, right? Because P is, let's say this guy goes, P is in the direction of the velocity, right? The angular momentum, we said, is pointing either this way or that way. Well, I guess it's pointing this way outside from the blackboard here. So the vector product of these two is going to point in that direction, right? Remember, they are always orthogonal. So P is pointing this way here, right? And you see, this is R, so it's pointing in the direction of R, so it's pointing in this direction. So this is MK R over R, this little, and this is P. Yeah, so A is the sum. Actually, there is a difference there. So between these two vectors, is pointing this way. So in other words, AA is some I don't know. It depends how is the difference between these two. So it's going to be a vector of this length. I don't know. How is it here? Well, here P is now is going this way, right? And R is going this way. So this is M K R R, right? So if P is going this way now, still the P cross L is presumably going somewhere this way, right? Because still, and you see that now A must be is this minus the other one, so it's a vector like this. This is A. Okay. And you see it remains the same. Points in the same direction, and the lengths too should be the same. And the same happened here. Now P is going up, right? And R still is going this way here. So this is M K R over R, right? Now if P is going this way, P cross L is somewhere in this direction. I have to take the difference. So now A is pointing this way. So you see, it just remains the same. It remains the same along the orbit. It's amazing. So that we saw it through the algebra, and here we see it through the eyes of geometry. The two. Okay, this was a footnote. I mean, you can forget about it if you wish. But
what this vector, the norm of this vector tells us?
yeah, nothing, I think. That's why I say it's just a footnote, because they discovered it and they got very excited because it looks like three more conserved quantities, right? Because it's a vector that is conserved. But actually, they are function of L, so it's not clear that they are independent. In fact, they are not. But okay, well, I don't know. I never use it in. This is the only place where I. It's the only place where. But I don't know. Maybe if you do some complicated orbit computations, but okay, it's kind of strange. Okay. So that said, let's go back to our main aim, that is to discuss a little more about this orbit. So, well, I gave you some exercises in which you are supposed to discuss the orbit for potentials that are not Kepler's. And in fact, well, that we will do it together on Monday. I want to discuss also the potential that goes like 1 over r squared, right? Remember that the one in terms of trigonometric functions were for the harmonical oscillators and the Kepler's problem, but also if the potential was 1 over r squared, right? So it's worthwhile to discuss also that case. There are forces going like 1 over r squared. There are forces going like many different powers, you know. It just happened that the two main macroscopical forces, that is electrostatic and the gravitational one, they happen to go like 1 over r. And so the Kepler's problem, by the way, if you know Coulomb law, right, it's just the same. So everything I'm saying here, it applies also to electric charges if it's a static configuration, right? It's just that you don't see that much because electric charges are perfectly balanced, so there is little force. If they were unbalanced, you will see enormous force, much stronger than the gravitational one. But because bodies in general, they are neutral, because you have as many positive charges and negative charges, so you don't see much of these electrostatic forces. But, well, we will talk a lot about this next year. Is there do we have negatively charged masses? That's a natural question, right? Because, where? No. In theory, yes. Sorry. No, not even theory, right? Because we don't have I mean, charges, we have positive and negative charges. But we don't have a negative mass. They have imaginary mass, right? Because they have a... Even if they exist, they do not. But so you don't. Gravity is always attractive. That's a very profound statement. But I mean, this is not the class to discuss this. But essentially, if gravity, I mean, if you can devise something with the anti-gravities, that would be very useful because you can make all kind of machines that work with zero energy, essentially. If you have, you know, because if you can turn that around, and that's the proof that you will never find anti-gravity, because then you will have a perpetuum mobile, you know, something that keeps on going on. And as you know, this does not exist because of thermodynamics. That is a different class. So, okay. So here I'm not sure how much we want to. I mean, once you. So let's now concentrate on this case here, because it's the most relevant, at least from the point of view of our solar system, because these ellipses, they describe the motion of all the planets around the sun. Now, this was really. I want to. I mean, if you don't know already about this, I want to stress the point that I mean, this was a gigantic leap in our understanding, because up to Kepler's, people thought that the motion had to be a circle. They thought, you know, in a way, the circle was our straight line. I mean, for us, the natural motion that is in absence of any force, as I said several times, is either you are at rest or you're moving with constant speed, right? You are in an inertial frame of reference. It requires no further explanation. I mean, if I tell you that you are there, your motion does not require any force to be explained. You are in a natural state, right? In this sense, natural in the sense that I don't need to tell you what kind of force is moving you. So for the people before Kepler, the equivalent of this, they had no idea about inertial frame of references. In fact, they thought that the F was equal mv. But for them, if something moved on a circle was the equivalent. It requires no further explanation. It was natural for everything to move in a circle. Now, it's a bit odd for us to understand this point of view, but many things, if you go to a different country, like you came here, I mean, many things looks odd. So, but for them, what was natural was to move. I mean, if they found something moving in a circle, they didn't need to tell you what kind of force was keeping those things moving in a circle. So, you see, for us, it's natural to see the Earth or the Sun going around to ask what kind of force is keeping the things there. Because for us, the Earth without forces would just move in a straight line. But for them, it was just the opposite. As long as the Earth moved, or the Sun is completely equivalent. I already said it 1 million times. It's just because people don't think that they are equivalent. But it was fine. They didn't tell you what the force was because it was natural that they would go around, okay? So that's very important because it's not that they didn't think about keeping the Sun there moving. It's just they, like us, it was a natural motion, so it was moving that way, okay? So they were not stupid. That's what I want to say. I mean, they were very clever, as clever as we are. So roughly, cleverness is a constant of motion. I mean, they were very clever, but they started from a different point of view. Unfortunately for them, okay, the first observation, you see, these ellipses, if you measure how much they are squeezed, they are not very much squeezed. Essentially, if you draw them, if I tell you what the eccentricity for the motion of the Earth around the Sun is, you will see that it's very, very small. Okay? So it looks very much like a circle. So if your level of observations is not very refined, it's fine. This is the fact that you say is moving in a circle is roughly correct. It's only when they start measuring with the better precision, they start seeing that it was not working that well, okay? And this is really what I want to communicate to you. It's only when you do, and we'll see what is the precision required to understand this, it's only when you measure things with very high precisions that you start really sometimes noticing differences. And now, I'm not talking about the fact that the Earth is going around the Sun, or vice versa, because that was clear. I mean, they understood that. I mean, they understood the fact that the planets were moving like this and then coming back. That's not difficult to explain, right? Because there are two perfectly equivalent and very satisfying explanation for that. That is, well, it depends if you prefer to put the Sun at rest or the Earth. If you put the Earth at rest, that in a way I prefer, then the fact that the planet, so the stars were moving on a circle like this, and the Sun likewise. And how about the planets? You remember they have this weird motion, okay? Well, that's not a problem. It's simply that the planet is moving on a circle about a point that itself is moving on a circle about us. And you see that if this is moving like this, what you see is something like this, right? And so sometime it comes back and goes up. So it was no sweat. I mean, they came up very quickly with this explanation. And you see, it works the same way if you put the Earth, and it's completely equivalent. Because it's a kinematical problem, and the kinematical problem only depends on the frame of references. So I'm not talking about this. This was clear. They knew that the planets were moving in this funny way because either they were moving about what they call the epicycle around a circle orbit. But you see, this is a circle and this is a circle. So fine. Circle on top of circle, very nice. In a way, they were doing Fourier expansions, you understand? You take any function and you expand in terms of periodic functions. And the periodic function here was the circle. So you see, they were far from being stupid. They were doing Fourier expansion. And the same works if you put the sun here, and then the Earth is moving like this, and again you have the same motion if you look at something else, right? So that works. The problem is that even if you do this, so let's do this. Let's do it mathematically and see why it does not work. So it takes a little bit of. So first I need the. So let me rewrite this in a nicer form. I just pull it up and down. You know about the semi-major axis. You know they work with geometry, so they needed. So you take an ellipsis, and then this distance here. So there are two foci usually, and this distance here, the total distance from the longest arm of your ellipsis, this is twice that distance, where A is called the semi-major axis, obviously, because this is the major axis, this is the minor, I guess, and half of this is the. And you know that this A is equal to the sum. If this is R1, okay, well, in general, right? So if this is R1 and this is R2, clearly A is equal to R1 and R2. Where R1 are also, you take the distance of your body moving around, is the distance with respect to the first of these two foci and the other one, okay? And you understand that this is true because if you take this very special case in which you are here, this is obviously true. And the only thing I want is to rewrite that equation in terms of this semi-major axis because that was a parameter that they were measuring through observation, right? Why this other thing, they didn't know about K, obviously, because they didn't know about Newton's law. So you want to rewrite the eccentricity in terms of observational parameters, and one of these is the semi-major axis. But this is quite simple because look at the, so let's take the equation and look at the, well, now I erase it, the energy. If you take the energy, you remember that we wrote the other time, it was R dot square. You have a question? You want to ask it, or? What is moving? What? No, this, for instance, this is the sun, and here is the Earth. So not the galaxy, it's just, but it works for any two-body problem. But let's consider, the most familiar one. So this is the motion of the Earth about the sun.
Where is the representation of the Earth?
Is this point here. Ça c'est la Terre. And here's the sun. So I take them to be just a point, and it moves around. And it's moving on this elliptic motion. I'm squeezing this way too much, as I said. Really, it's very close to be a circle. And you remember the energy was the kinetic term, but let's take the energy when, for instance here, where the r dot is equal to 0. So then the energy minus the angular momentum, you know the effective potential, 2mr square plus kr is equal to 0, right? Go back to your notes. A is the semi-major, so is this distance. So 2a is the distance, is this. So A is half of this. So you see, so 2A is R1 plus R2 by definition. And so 2A is the major axis of your, and A is half of it, so the semi-major axis. So you see, this is just I want to rewrite the eccentricity in terms of quantities that you can measure by looking at the planet. And the trick is now I can solve this because this is a second order algebraical equation. So this is r square k over e r minus L square 2me equal to 0, right? I multiply by r square, divide by e, okay? And this is what I get. And you know that the sum of the roots of these equations, or minus the sum of the roots, is equal to this coefficient. It's one of those neat things that, if you remember, and if you bear those in mind, it's neat. So you see that minus R1 plus 2 is equal what we call 2A. So from this I can get that A is minus K over E. So I succeed in rewriting K in term, well, K over E in terms of A. So if I use that, you see that the eccentricity now is E, well, I write it, E is so E was 1 minus L square MKA. Okay? And that means that L square mk is equal A1 minus A square. So now I can rewrite the equation of the ellipses all in terms of geometrical quantities. That is what I want to do. So 1 over r, I like it better written like the orbit is, so let's take 1 over, so r is equal, okay, you see you have the A1 minus A square, that is L square mk. Remember what C, right? So I can rewrite C is equal to this. So I rewrite C, well, 1 over C really is this, right? And then downstairs I have 1 plus E cosine theta minus theta naught. Okay? So this is 1 over C, so I took, okay. Now what? So this is the equation for the ellipse in terms of, so these are things that people measure by looking at the motion of the plane. The eccentricity, right? and the semi-major axis. So in terms of these two, the orbit was completely defined, and you could find the one. Now, if you observe, so this is the orbit, but if you sit and observe the motion of a planet, really you don't see the orbit, right? You see the trajectory, because you are sitting here, and night after night, you look at the position of the planet in time. So you're not seeing the orbit, you're seeing the trajectory. So in fact, what you're seeing is not the r so much, but the theta, right? How it's moving on this sphere. So we really, to put ourselves in this old people, I mean, in their shoes, we need to look more at the how it's called, the trajectory. So let me write so you remember the equation for the trajectory? It was t was some constant that we call it like this, r square d theta, right? That by using this, so now I want to find what is the trajectory if I'm moving on the orbit that is ellipsis. So I plug in this, I have this constant, and then I have a square. This is another constant, if you wish. That's it. And then you have to integrate the square of this. So d theta 1 plus e cosine of theta minus theta 0 square. So to find then you invert and you find the theta as a function of time. So is this a easy integral? Are you going to find this integral in your tables? Probably not. It's a complicated integral to, well, try. No, I mean, not now. Just you have the weekend to try. Anyway, this is it's a complicated integral, clearly. You agree? No, not very, but sufficiently complicated that this is the integral that Kepler found. I mean, he assumed, the first law, Kepler's first law was that planets were moving on ellipses. No. So he knew this, he plugged it in here, and he had to do this integral. So the one way is the way probably he did it. So first, let's simplify this integral. Okay. You see, if I call these things so, I mean, when you try to solve an integral like this, you try to do a change of variables, right? This is sometimes it works, sometimes, well, very often does not work. But let's try this. So I take this, and I call it. So this was a certain angle, and I introduce a new angle. Okay, so this psi is a new angle. And okay, I hope that by this transformation, in a way, you see, this looks nice, because if it had been without, it may looks like it may work. It won't work, but it may work. So if I do that, you see that. So let me maybe you check the steps. So my claim is that if you change your variable from theta to psi through this change of variables, this integral becomes this other integral here. MA cube K 1 minus E cosine psi d psi. So maybe I'll leave it as an exercise because I want to, because it's Friday. So maybe on Monday we come back to this. If you try to, but it's not difficult. I mean, you see, this is the change of variable. So you have to compute d theta, right? This is the way it works. I mean, this is the change of variable. Now you have to find what is d theta as a function of d psi. And you see that this is something like this. Maybe I give you this that helps. So you see, this looks very nice because you get 1 minus E cos psi, so you bring it on the other side, it simplifies, and you are left with this. How do you find this? You have to write the cosine of theta as a function of the cosine of psi, right? But this is simple. You just invert this algebraical equation. When you have the cosine of theta that, then you take the differential and you get this. Now, if you take this, you change the variables, you get to this expression here. Now, this looks like it really worked because, you see, this is a trivial integral now that even I can do because it's the integral of d psi and then the integral cosine of psi. Okay, I guess even without the tables of integrals, we know how to do that, right? So this, you see, can be integrated. Let's call this 1 over omega. It's going to be a frequency just by looking at an angular frequency. So you see, the solution of this is that psi minus E sine psi, right? I do this integral, so E psi, E sine psi, obviously, is equal to, well, I have 1 over omega, I bring it there, omega t. So apparently I succeed. This looks an awful integral. I did a clever change of variables, and but okay, this equation is called the Kepler because this is the way he obtained Kepler's equation. And if you solve this, well, this is essentially solved. But you see, it's not a completely trivial equation because you have the sine and psi, so it's a transcendental equation. It's not just something that you solve easily, right? But you do an expansion and you solve it. I want to do this expansion, but let's see if we have time. But I want to just to point out that as you know, if something is difficult, it's not going to become simple just by a change of variables, right? It's not that if you give a different name to a bad dog, the dog is becoming, a good dog. There is a conservation of difficulties, and you understand that the problem that you solve this, and then you have to go back. This is the usual problem with doing integral through a change of variables. That then you have to use the change of variables to go back to the original variable, because at the end of the day, you don't want psi as a function of t. You want theta as a function of t. Okay, so you still have to rely on this change of variables. But okay. So if I solve this, essentially I've solved the problem. Are you still with me, or yes? Okay, I take 10 more minutes, then I let you for the weekend. So I want to solve this, and I want to show you what happened. And how do you solve this? As I said, this is a transcendental equation, so it's not such a simple thing. You have to do it numerically, essentially, right? Or by expansion. That is more or less the same thing. And so one way to do it, the way computers usually do, you do by reiteration, right? You assume that this is sufficiently small that you first write the leading order solution. So, I mean, you can try and start. So if this is small, a good approximation is going to be this, right? I mean, this is small. Then you plug in the solution in the original one, and you find the next order. You understand? Right? So this is the leading order. The next order is going to be what? This plus the term that you neglected. And so on and so on. I mean, it's really an infinite series. And if E is sufficiently small, you may hope that it's converging fast enough that maybe the first two steps already give you. In fact, as it happened, the first two terms are sufficient for the precision level of people in the 1700, 1600. So, yes.
Why there is not constant?
What constant? You mean an overall? But that depends the way you start. I mean, I start in such a way that the T0, I mean, is 0. So when you integrate, you have a T0 here, but I start counting from the moment you start looking at the sky. So, okay, this is another interesting exercise that you can solve this equation by reiteration, and you see the building up of the solution. So if you do that, you are going to find psi of t, and then through the change of variables that I just erased, you plug in psi of t, and you get theta of t. That is what you actually see. And the point I want to make is that if you do that for the ellipses, you find theta of t, that is your trajectory, and what you find is omega t, that is just this leading term. So I'm doing an expansion. And then one correction, that is 2e sine omega t, that is the term that comes from here. And if you go one step further, you find 5/4 e square sine of omega t plus terms, okay? And now you see why I was talking about, in a way, Fourier series, because you see it's a sort of, right? So I'm expanding this motion in a Fourier series, and these are the first three terms of this expansion, okay? But it goes all the way, see? Okay? So this is the solution that Kepler found. What was the solution that Ptolemaios had? Ptolemaios is the guy who championed very much this idea that there were circle within circle, right? You know. In fact, he is the guy who wrote the Almagestum, that was the best stellar catalog up to the time of Tycho Brahe. Just to make a little, Tycho Brahe, you know, have you ever heard this guy? This was a guy in Denmark who improved by 1 order of magnitude the precision in the position of the planets and the stars. And I'll show you why this was a breakthrough. You see, if you go back to the Almagestum, this is a beautiful book. It had the position of all stars, and in particular all the planets. for each day, right? You still if you go to the internet, there are the equivalent of the Almagestum. Now you ask where today, tonight, for instance, probably it's going to be a very clear night. So if you go out, you may, where is Mars, the planet Mars, tonight? And you look at this, and they tell you, look that direction with that, these two angles, and you'll find the planet at 11 o'clock. Then at 12 o'clock, it's going to be there. So the Almagestum was the equivalent of this, of these things that you find on the internet now. And so they need to know all these positions, and essentially they had all this stuff, but what formula they were using. So now it becomes a little complicated, but let's just make it short. So I said they put the planet, so they had the planet on an orbit. And this orbit had to be a circle, because they wanted to be a circle. Because otherwise, if it was not a circle, they would have needed a force, and they didn't have any idea of how to produce this force. But it could not be exactly on a circle, because if you do that, I said, you look at the position of the planet, and they are off immediately. I mean, they are not off. So this would be the circle, right? Omega, some angular velocity, then it goes around, around, around. So if you're not very careful, this is okay. If you a little bit more precise, and the precision has to do with the eccentricity here, and I said it's small, but essentially if your precision is of 1 degree, that's very, very small, right? Then if that is your precision, you start seeing this. And this is tenths of degrees. Now, if your precision is of 1 degree, that is essentially the precision they had at the time of Ptolemaios, because they had, I don't know if you've ever seen, they had this huge, you have to look, so essentially you need something to measure angles, and you know that the bigger the machine is, the more precise the angle is measured, right? You understand this? Because if you have something like this, I mean, roughly you have no precision at all. But if this is as big as this building, essentially, is the precision with which you can make this. So if you go around the world, these machines are still around. I think in how is called that place? But in India, there is one place that I forgot the name of, Jalapur or something. Well, okay. And there it's very nice. You go there, you see this huge ladder where you sit, and there are many marks on this, so you can measure angles. So you look, and in Samarkand, that's well, it's not Russia any longer. It's another of those countries. You find another one of the largest. So these people measured the position of the planet with this precision, and they realized that so it was not moving like this, so they needed further things. But they wanted these things to move on a circle. So how do you do it? So essentially, it's going around, and say the Earth is here. Let's call it T for terra, that is la terre, like in Italian is the same, so we call it T. And so the first thing they thought is that, okay, it's going around the circle, but the circle, the center of the circle is not about the Earth, but about another point. Okay? And then you see, that's very clever, I mean. And that's where the name, the eccentricity. So this was called C, the eccentricity. So this guy is going around in a circle. It just happened that we are not at the center of the circle. We are a little shift. Okay, is that clear? You want the thing to move on a circle, right? We all agree on that, or not? Because I said that if it moves on a circle, you need no force to keep it moving. Okay, so I want it to move on a circle. But I know, because of my observation, that it's not moving on a circle, because of two reasons. First, it's not following a circle. Second, even worse, the velocity with which it's moving is not constant. because they saw that it's moving faster in the winter and slower in the summer. And you see that if this is the only term, the velocity is constant. But if you have further terms in the Fourier expansion, this thing is going to move at different velocity. So you need these two effects to be taken into account. And so one way to do this is to move the center of your circle away from us and assume that it is moving in a circle, but not about the Earth, about another point that was called the eccentric. But if it's moving this way, still is moving with constant speed, because still is moving on a circle, okay? So they had to further assume that not only is moving about this other circle, but it is moving in a uniform, with the uniform speed, but about not C, but about the third point that was called the equant. So this is really weird, it's becoming. It's moving about a circle that is not centered on the Earth, with a speed that is constant as seen for a third point that I call the equant. If you do these three assumptions, okay, you get that, you call this distance here E1, and this distance here, I call it E because it's related to the eccentricity. You call this E1, E2. You do the math, okay? And what you find, I did it here. It's a bit long, so we are not going to do it. I did it somewhere, but yes.
What does it mean, equant?
In
A name or that's
equant. I don't know.
maybe there are reasons when they call.
Equant. Yeah, the root is the same as equal, but I don't know. You may check on the internet, on Wikipedia, I'm sure you. You also have to find the factor of 2. I don't know if that is on the Wikipedia. I did the computation, but I think I left it in my office. Anyway, I write the result. Yes, it's here. So now you do this computation. So what is theta of t for this weird thing that they came up? So clearly you start out with the same term, because it's the approximation in which you neglect the fact that there is this double splitting, right? Then the first correction due to the to that goes like E1 plus E2. The sum of these two distances, sine of omega t, plus 1/2. Actually, I think it's minus 1/2 E1 plus E2 sine of omega t, and you keep on going. I mean, this is not the computation they did. I'm redoing their computation in our modern language. And so then you try and fit your data, and the fit is such that E1 is a very good fit if you have E1 equal E2. So these two distances are equal to the eccentricities that is something that you measure. So you see, you get here 2E, and here you get 2. You get 2E squared, so you get minus E squared. So, as I said, Ptolemaios was able to work with the precision of the order 1 degree. So he was able only to see this part of the orbit. It was part of his systematic error, this stuff here. And so you see, it works, okay? You see, you get this, and you get the first order. So the Almagestum, up to this order, was perfect. If you were blind to anything below, I think, 4 degrees, I don't remember, but I mean, the order of the 1 degree, you are fine. So up to Tycho Brahe, who built an even bigger machine, unfortunately, they are all destroyed. He was given a small island between Denmark and Sweden. So he was the king of this little island. And there he built this many machines to help him to measure. And he was the first guy who started seeing with more precision than the degree. So he started probing these terms. And he worked for many years. At the time, there was no TV, so at night he was just watching the sky and mapped the motion of many planets, and then he compared the orbits with this formula. And you see, this is the beautiful thing. At this point, he starts seeing. So he was expecting -1, but we know that they move in such a way that this coefficient is 5/4. So he was the first person to realize that the system was not working. Even if you add this equant to the eccentric, you really, you are stretching a little bit, but still moving on circles. You could not make it. You are not fitting the data. The data are telling you that something is profoundly wrong. And we know that what is profoundly wrong is that there is no way that a finite number of circles give you an ellipsis. You need the infinite Fourier series to get the real orbit, and things go wrong very quickly. Of course, I can add some other things here to get this, but you start losing faith at this point, because each time you improve your measurements, you have to add the circle, and this is a signal that something is wrong with the theory. And Kepler was a student was an assistant of Brahe, and he got all the data when Brahe died, and he, after working many years trying to improve these things with the circles, suddenly he realized that if he put a ellipsis, he got the correct coefficient, and all the data suddenly fit. And he had discovered, essentially the correct orbit for the gravitational problem. And remember that, as I said the other time, if you know the orbits, in a way, you know the force at that point. Because through the Bertrand theorem and all these steps, you can go back and understand that this motion must be produced by 1/r². So he almost got Newton's law of universal gravitation. And I think this is a great lecture for, to learn the lesson that, you have to look in the data and use those and to do that you need to look really in the details. You see here it was hidden at the third order, first, second, leading, first correction, next to lead in order, and only when you had that precision, you got the law of universal gravitational force. Okay.